Hi everyone, it's B again. In this lesson, we'll be learning about some very interesting concepts that arise in the context of finances. On the cover sheet of your PDF, you had this pre-video exploration. If you haven't had a chance to work on it yet, pause the video to do that now. Now, let's analyze it together. The problem reads, you are trying to pick a bank account that would earn you the most interest over the course of a year. You are only depositing $1, and the bank is giving you the following different options. Account A earns 100% interest once a year. Account S earns 50% interest twice a year. Account Q earns 25% interest 4 times a year. Which account would be your best option? Explain your answer. To figure out which one is better, let's find the balance that each one would produce after 1 year with your $1 deposit. In your guided notes, you'll find this table that will allow us to compare the behavior of the accounts side by side. But first, if our goal is to find the balance at the end of 1 year, what would be an appropriate time unit? Since each account earns interest a different number of times in a single year, let's use months to comfortably work within a single year. At 0 months, all the accounts start with $1. To find the balance in account A after 1 year, or 12 months, we need to add 100% once, which is the same as doubling, resulting in a final balance of $2. For account S, we need to add 50% twice a year. But wait, isn't that just the same as adding 100% once, like we did in account A? Let's see. We can add the first 50% halfway through the year. That is, at the 6-month mark, and then the second 50% at the end of the year. We add 50% by multiplying by 1.5, so at month 6 we get $1.5. But then the second 50% we add will be from the new balance of $1.5, which results in $2.25, more than in account A. Why did we get different results? Because adding interest in 2 separate instances made the second increase build on the interest already earned from the first increase. What do you predict will happen in account Q? Will we get an even larger amount? Adding 25% 4 times in a year would be equivalent to multiplying by 1.25 at months 3, 6, 9, and 12, which gives us around $2.44 at the end of the year. As expected, we get even more money. Therefore, we can confidently say your best option is account Q, since after 1 year, account Q yields $2.44, which is the most money out of the 3 accounts. This result may have seemed surprising. At first glance, it might have looked like all these accounts were all just adding 100% in a year, since 50 times 2 and 25 times 4 both give 100. But the more this apparent 100% increase was broken and applied in separate pieces, the more the balance grew. This phenomenon is the key idea behind what we call compound interest, which is the interest that builds on previously earned interest. Compound interest is used to grow savings and investments, and also credit card debt. So you can see why it's important to understand it. Compound interest accounts operate with 3 different parameters. The first one is what we call an annual interest rate, R, which is broken evenly into separate increases made throughout a year. Therefore, all our 3 accounts are considered to have the same annual interest rate of 100%, which written as a decimal is 1. The only difference between them is the number of separate increases that it was broken into, which is also the number of times the increases are applied, or compounded, in a year. We call this number the compounding frequency, n, which is the second parameter. For account A, we say the interest is compounded annually, that is, n equals 1. For account S, it is compounded semi-annually, which means n equals 2. And for account Q, it is compounded quarterly, that is, n equals 4. Lastly, our third parameter is the principal, P, which simply means the initial deposit. For all three accounts, the value of P is 1. Now we'll see how we can use these three parameters to write equations for the balances in these accounts after any number of years. Let's name these functions A, S, and Q of the time t, which we will now switch to years, as it is the preferred unit in financial contexts. We will specifically focus on one of the accounts, the best one, account Q. Does the behavior of this account remind you of a certain type of function we've seen recently? This is an exponential function because the outputs are growing by a constant factor. We know, therefore, the function will be in the form of an initial value times a growth factor to the power of t. Pause the video and try to write the equation for Q. Remember that since our time is in years, you need to use a yearly growth factor. The initial value is just our principal of $1, and our yearly growth factor would be 1.25 to the power of 4. What are the roles of P, R, and N in this equation? Well, P is right in front as the initial value. I also see the N as the 4 in the exponent. But where does the 1.25 come from? Remember, the 1.25 represents 125%, which is the factor that adds the 25%, which came from dividing our annual interest rate of 100% by the compounding frequency of 4. However, to get the 1.25, the percents need to be written in decimal form. So instead of 100%, we write 1. Now, let's write a general formula for the amount of money A of t after t years in a compound interest account for any given values of P, R, and N. Using the structure of function Q, pause the video now and try to write this general formula yourself. The formula would be A of t equals P times 1 plus R over n to the power of n times t. It's important to note the value of R needs to be written in decimal form. Using this formula with accounts A and S, we would get these equations, which would simplify to A of t equals 1 times 2 to the t, and S of t equals 1 times 1.5 to the 2t. Notice how these perfectly match with the yearly growth factors we could have gotten from our table. Let's now put this formula to work with a question about some other account options. The question reads, how much money would you have after 1 year if you deposited your $1 into an account earning 100% annual interest compounded monthly? Compounded daily? What results are you expecting? The interest in these accounts is being compounded more frequently than in our previous accounts. Therefore, we'd expect amounts larger than $2.44, which was the amount compounding quarterly. Pause the video and try to find these new amounts yourself. Compounding monthly would mean 12 times a year, which means n equals 12. The balance after 1 year would be 1 times 1 plus 1 over 12 to the power of 12, which gives around $2.61. Compounding daily would mean n equals 365, so our balance would become 1 times 1 plus 1 over 365 to the power of 365, which gives around $2.71. Are these results as large as you expected? From compounding 12 times a year to 365, there is a huge difference, yet the balance ended up being just around 10 cents larger. Let's try compounding even more frequently. How much money would you have if the account compounded 1,000,000 times a year? Pause the video and calculate it yourself. Compounding 1,000,000 times a year, we'd only get around 2.72. What a tiny difference! Here are all the results we've obtained using various compounding frequencies from least to greatest. What do you notice? It seems like as we increase n, the result keeps increasing, but by less and less every time. Does this behavior seem familiar? Let's forget about the 1 in front since it's not really affecting the values of the expressions. As n gets larger and larger, the expression 1 plus 1 over n to the power of n seems to head toward a specific value. If we graphed this expression as a function of n, the curve will show a horizontal asymptote just slightly above 2.71828. The exact number this expression approaches is actually a very special number in mathematics called Euler's number, which we represent with the letter E since it is irrational and we can't write out its decimal form. The number E is named after the Swiss mathematician Leonhard Euler, who made huge contributions to the various fields of mathematics. One formal way of defining E is as the number that 1 plus 1 over n to the nth power approaches as n approaches infinity. Does this description remind you of something we've learned about recently? This statement is simply the end behavior of this function. A fancier way of defining E is using limit notation, which you were introduced to in Unit 2 as another way of expressing end behavior. We say that E is equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power, which is around 2.718. This statement is saying the exact same thing as our first definition. As n goes to infinity, 1 plus 1 over n to the n is getting closer and closer to E. Furthermore, remember how that 1 on top of the n originally represented an annual interest rate of 100%? Here's another very interesting property of E. It turns out that if we replace that 1 with a general interest rate r, as n approaches infinity, the expression approaches e to the r. Written in limit notation, e to the r equals the limit as n approaches infinity of 1 plus r over n to the n. This leads us to a new ultimate type of compound interest. Let's bring back our compound interest formula. Now we know that as n approaches infinity, this growth factor gets closer and closer to e to the r. Therefore, if it were possible to compound the interest infinitely many times in a year, this equation would become exactly a of t equals p times e to the r to the t. Multiplying the r and the t, we get a of t equals p times e to the rt, which gives the balance in an ideal account where the interest is compounded infinitely many times in a year. That is, every single instant. Since we're compounding the interest non-stop or continuously, this type of compounding is known as continuous compound interest. The meaning of each parameter in the formula stays the same, but now there is no n because we took it to infinity. Going back to the discussion about your account options with the $1 deposit, if you were able to get an account that compounded the interest infinitely many times per year, we would say it's being compounded continuously, and the equation for the balance would be c of t equals 1 times e to the 1 times t, or just e to the t. How does this type of compounding compare to the other ones we tried? With your $1 deposit and 100% annual interest rate, continuous compounding would be your absolute best choice, as it would yield the maximum possible earnings. Since e to the 1 is just e, the maximum possible balance you could get after 1 year would be $, which rounds to $2.72. Let's apply the formulas we've learned in an example problem. Example 1 reads, Jack and Jill went to the bank and they each opened a compound interest account. They both made an initial deposit of $2 and got an annual interest rate of 6%. But Jack chose monthly compounding, while Jill chose continuous compounding. Part A says, write a function for each account that models the balance after t years. Pause the video and try writing the functions by applying the formulas we've learned. Here they are for your reference. Our input would be the time in years, and for Jack's account, let's call the balance k of t. Since his interest is compounding monthly, we use the normal compound interest formula with a principal p of $2, an interest rate r of 6%, which we must write in decimal form as 0.06, and a compounding frequency n of 12. Simplifying this formula, we get k of t equals 2 times 1.005 to the power of 12t. For Jill's account, let's call the balance j of t. Her interest is compounding continuously, so we use the formula for continuous compounding. We again have p equals 2 and r equals 0.06, so we get that j of t equals 2e to the 0.06t. Let's look at part B. When will Jill have $10 in her account? Pause the video and try to solve it yourself. Here's Jill's equation. We replace j of t with 10 and then divide both sides by 2. Since e to the 0.06t equals 5, then 0.06t must equal log base e of 5. But wait! Since e is such a special, naturally occurring number, log base e has its own special name and notation. The logarithm base e is called the natural logarithm, which we shorthand as ln, and it has its own button in all scientific and graphing calculators. So instead of log base e of x, we always write ln of x. Therefore, let's replace this log base e of 5 with ln 5. Lastly, we divide both sides by 0.06 and get that t is around 26.8. Therefore, Jill will have $10 in her account after approximately 26.8 years. In today's lesson, we learned a lot about compound interest, which is when an account earns interest on interest. This led us to this very interesting naturally occurring number called Euler's number, or E, which allowed us to develop a formula for continuous compound interest, which happens when we apply an infinitely small portion of the interest rate infinitely many times throughout a year. In the next lessons, we'll be using E in several different real-world scenarios and learning all sorts of cool applications. Once you've finished your guided notes, complete the additional practice in your PDF. After that, make sure to complete the online practice. See you next time!
Hey, hey.